I thought this was supposed to be um, already about planar code, but it seems like it's still about the toric code. I don't know. I feel a bit in a rush to some extent these days. Uh, I don't know. Let's just go through this. Previously, in this series, we looked at toric code, fairly simple quantum code for us to understand, but not as simple. So actually build, making a bunch of qubits and then using them as the icing on the donut. One of the easiest things to experiments. Firstly, by flattening out the toric code, we can get the so-called planar code. Okay, so indeed there's something about planar code which is just as good or half as good, depending on how you measure goodness. But this post is not going to be about planar code. Okay. First, we'll look at a nice story that can be told about these codes that can help understand them without needing to pore over all the little details. This is a story of anions. Rule breakers in the toric code. The toric code is a bunch of qubits sitting on a grid. For each big white square in the grid, there is a rule. When errors happen, rules get broken. These traces left by others, I will find to correct them. Yeah. How exactly the errors cause broken rules? In the picture below, an error has happened on a single qubit, the one shown in red. This has caused the two rules to be broken. Those for the big white squares either side. This happens whenever we get a single isolated error. It always causes the two neighboring rules to be broken. What happens in more complicated examples where some rules are already broken? The rules that state the numbers around the numbers around each big square, white square, should add up to an even number. Every error flips the two neighboring squares from odd to even to odd. This means it flips the squares from being rule obeyers to rule breakers or vice versa. So suppose another error happens around one of the rule breaking squares from above. The previously rule-breaking square now obeys the rules again, but another square is made that breaks the rules. So the new error has effectively moved the broken rule from one place to another one. How about an error that happens between the rule breakers? If an error flipped the pink 0 below to a 1, both of the rule-breaking squares will be returned back into law-abiding citizens. This is the exact opposite of when errors create a pair of rule breakers. Here it effectively moves them together, causing them to cancel each other out. Okay. Particles in real life, as you probably already know, things are made out of atoms, and atoms are made out of protons and neutrons and electrons, and protons and neutrons are made out of quarks. So everything we know and love, like chips and stars, are made out of the electrons and quarks. As far as we know, electrons and quarks aren't made out of anything. They are known as elementary particles. Another important elementary particle is the photon. This is a particle of light. Unlike electrons and quarks, photons have no mass and no electric charge. They just zip around at the speed of light, hardly interacting with anything, unless they bash into it. Then whatever they heat absorbs all their energy and there's no more photon. This makes photons more like little blobs of energy than a proper particle like electrons and quarks are. You can't make chips out of photons. The electron has a brother, an evil twin, the positron. If an electron and positron ever get too close to each other, they annihilate. All their massive energy disappear and burst of light. In a burst of light, the opposite can happen too if a couple of pretty energetic photons meet. That energy can turn into an electron and a positron. This all might seem a bit like getting something from nothing, but because those two somethings add up to nothing, the universe seems to think it's okay. The positron is an antiparticle of the electron. The electron is the antiparticle of the positron. All particles have antiparticles. So some like electrons and positrons, they're antiparticles. Antiparticle is a different type of particle. For others, the antiparticle is any other particle of their own kind. So if these ever meet a particle like themselves, they will instantly annihilate. Rule breakers as particles. So what have we seen so far? Broken rules in the toric code are created in pairs and they can be moved around. If two are moved together, they cancel each other out and disappear. Particles are also created in pairs and can be moved around. If a particle and an antiparticle are moved together, they cancel each other out and disappear. So broken rules in the toric code behave a lot like particles. They anticipate the antiparticle. The antiparticle of a broken rule is simply another broken rule. Of course, they are not real particles in the same way that electrons or even photons are. They are examples something we call quasi particles. They are just things that we can understand by telling the story that they are particles, they won't pop up out of the toric code and start interacting with real life electrons, and any more than Harry Potter will jump out of the book. But within their own little universe of toric code, it makes perfect sense to think of them as particles. Bosons, fermions, and something else. I don't know. It seems so far unrelated, but it's pretty nice read. All particles in our universe are either bosons or fermions. Electrons, positrons, and quarks are fermions. Photons are bosons, as are Higgs bosons, as I'm sure you won't be surprised to learn. What about our rule breakers? A little analysis shows them to be bosons, the most boring type of particle. But we should remember that the blue squares have rules too. These are another kind of particle that live in the toric code. If we look at how the blue square rule breakers play with a white square, we'll find some strange things happening. Breakers play with a white square, rule breakers will find some strange things happening. Things that particles in our universe never do. They aren't bosons or fermions, they are anyons. But what is an anion? That we'll have to wait until next time. But what the in between, you mean anions because of the interactions between the blue squares and white squares, or what? Look at how the blue square rule breakers play with the white square rule breakers, we'll find. Okay, then let's take a look. I wonder why these things are not linked. This is 11, so I'll just go to 12. Although, I don't know if it is. I don't know if I should take a look at this. So here says whatever the game, which I have to take a look at. I kind of read this yesterday. Maybe I'll play with this a little bit. And then there's another blog with anions. But I don't know if this is something I can skip. Or is it something mandatory to anions in the real world? An anionic quantum computer. Quickly scan through that. So I don't know what anions are. I'm surprised. Want to know how we could build a quantum computer from them, then read on. Indistinguishable particles. Every day we see objects to cancel cake roll on the same production line. They create the exact same process, but there's different lots of them. These are indistinguishable, and in practice and in principle, they're exactly the same, so much that it has been proposed that the universe actually only has one electron that zips forwards and backwards in time. Crazy. What is this? Like, one electron universe. Really? Crazy. Suppose you and your friend each have a can of Coke, your weight 36 grams, and your friend's weight. And so now you have one wedding. The situation after the sub is different to the one before, not by much, but different all the time. Not suppose instead you have an electron in a box. Don't think too much about the boxes though. They're just there for the stories. It's the electrons that matter. So you each have an electron, then you swap them afterwards. You again each have an electron. Since electrons are identical, it is exactly the same situation as before you swap. The laws of physics don't allow anyone to work out whether you did the swap or not by just looking at the electrons because they are identical. What if someone comes along and shuffles the boxes and gives you one back at random? Do you end up with the same electron or a different one? The best answer you can give is that it is indeed one of these two possibilities, but which one? Even the laws of physics, even if you watch the shuffling very carefully, you still can't be completely sure. Electrons are quantum things. You can never know exactly where quantum things are. It's entirely possible that electrons swap boxes a few times just for fun. So even without the shuffling, the electron is in your box. This phenomenon of doing two contradictory things at once is uncommon for quantum particles. It's called quantum superposition. But usually it only lasts until you look at a particle. It has to decide which of the things to be. But since electrons are identical, you can look at all you like, and you'll never find out whether it is the same or different. So they will keep their muddled identities forever. It's quite an odd thing that you can do something fairly big, like swapping a couple of particles, and yet the universe contains no trace that you did it. But then physics gives us odd things we can often use it for stuff. So let's see what this property will do for us. Okay. Swapping superpositions. Electrons are quantum particles, so they can be in quantum superpositions. This allows them to be in two places at once or do two things at the same time. We've said that electrons must be identical, but there's no reason for their superpositions to be identical. That's an interesting statement. So now, say that your electron is in a superposition of being in your box and being at home, and your friend's electron is the same. Then you swap your boxes without looking at whether the electrons are there or not. If both boxes were empty, you swap nothing with nothing, so nothing happened. If both had electrons, it's as if nothing happened too because they're identical. But if you had an electron and your friend didn't, after the swap, he has it and you don't. You had an electron and your friend didn't. After the swap, he has it and you don't. That's definitely different. But what about the superpositions? To make it easy to see the effect of superposition alone, let's swap twice. Then everything ends up where it started, and superpositions are the only things that could have changed. Now we've got to start talking about how to. So, if you type, if you did the second swap by giving your left hand, the right, you would be doing the exact opposite of the first swap. It would look exactly like you're going backwards in time and doing the first swap. So the result of these two opposite swaps will have to be nothing. Everything you did, you undid. Now suppose you do the second swap is exactly the same as the first. Give the right and receive the left. To work out what happens after two swaps, the same time we'll need some topology. When you start your boxes, you will probably intend to do it with a gray source with movement. But alas, our truncated movement will be at least a tiny bit wobbly. This doesn't matter though. A swap is a swap, wobbly or not. In more mathematical terms, it is only the topology of the swap that matters, not the exact details. For example, suppose that we had two particles that once were together but then got separated and later came back together again. Their journey through space and time can be represented by the picture on the left below. The two particles at the bottom are the particles together in the past. Those at the top are the particles together now, and the lines show how they drifted apart and then back together. Show different paths. The next picture is the same thing but slightly changed. The movement of the particles is a bit more wobbly, but often you can agree that that's a basic story. The next picture is a slightly changed version of the second, and so on. At some point, the particles swap around, but then they unswap a bit later. So again, it's still the same basic story, but no swapping really happening. Because of this, we say that these shapes are all topologically equivalent. To now consider the two pictures below instead. These tell a very different story to the one before. They both have a single swap. They also tell a very different story to each other since the swaps go the opposite way. Do they? No, they don't. There's no way through lots of small changes to turn one of these pictures into the other. There is no way to turn the pictures both with no swaps because of this. We say that they are all topologically distinct from each other. So topologically equivalent trajectories of particles through space and time. So through space-time, you probably didn't think you'd be reading this phrase today. Tell the same basic story of what kind of swaps happen. And topologically distinct trajectories have different kinds of swaps. But what does it tell about the problem? What happens when we do two swaps? In this picture, we start off with two swaps on the left, and then by little changes, we end up with something quite different on the right. One of the particles does nothing. It just sits there. The other one does all the work, rotating all the way around the lazy particle until it ends up back where it started. So two particles swapping twice is the same as one particle looping around the other. This is about the process. Let's imagine what is it getting to? Nothing. I think are called bosons. Photons, the particles of light, behave like this. So do Higgs boson, obviously. Particles that get some minus ones in distribution are called fermions. Electrons, protons, and neutrons are all fermions. If we lived in a 2D universe, though, maths would not be so strict. We could get almost any kind of crazy stuff happen when we saw particles. Particles that behave like this we call anions. These are okay. So there's this game. Abelian onions are only a tiny bit stranger than Boston fermions. There are a set of rules. There are several rules for what kind of particles your composite will be given the particles they combine. This is far too. That's not putting onions to work. So particles in the first strong composite. If the right pair is 0, then the left pair is moving the particle around nothing, so nothing happens again. The only time that something will happen is if both beats are 1. Then we're taking Fibonacci anion around Fibonacci anion, and weird quantum stuff happens. This is similar to something called the AND gate, which is used in normal computers and can be built from a couple of transistors. There's no obvious problem with building an anionic quantum computer. We don't have there's one obvious problem. Any anions they are not allowed in our boring 3D universe. Fortunately, there is a way around this. Our universe can have 2D things inside it, so maybe we can build a 2D universe in the lab. It sounds like sci-fi, but it's possible. In some materials, you can get excitations, like little clumps of energy that behave just like particles. If you have a 2D material, so that these fake particles can move in two directions, it can turn out that they can behave as anions. For example, I do it with dice in this video.
Hello, I'm Dr. James Wotton of the University of Basel, and I research quantum error correction, and specifically topological quantum error correction. This seeks to keep quantum computers free of errors using particles called anions. The trouble with anions is that they don't actually exist in our universe, and they're actually kind of impossible in our universe, because our universe has 3 spatial dimensions and they can only exist in 2D universes. However, we can force them to exist, and in this video I'll be telling you a little bit about how to do that. Normally we would use quantum systems to do this because they have nice quantum properties that we can use, but today I'll be using dice. We can do half the job with dice. Unfortunately it's the easy half, but it's enough too much about how lower it is than a multiple of 6. 2, so it's 2 higher than a multiple of 6. And just to keep track of the ones that we're messing with, let's also...
So now it's your job to build one of these things. If you want to help us, you can. That's why this project is all about. So here for more details. So this is what the game, what this game is all about. But basically, this is, I might come back to this. We'll see. I might come back to this. So this is sort of explaining you what these anions thing are, which is basically something that doesn't exist in our universe, but it's just it describes a certain behavior that happens when you go down to 2D. So let's see what's in here. So it goes all the way to 13, the planar code. Okay. So last time we showed broken rules into our code behave like particles. The white squares have one type of particle that are created, move around, annihilated using beat flips. The blue squares have different types of particle, which is manipulated by phasors instead. Since then, we also published an article about anions. Okay, that's what we just saw. These are strange particles that do strange things when they dance around each. Anions are impossible in our 3D universe, but the surface code is 2D universe particles. Could they behave as anions? It turns out that they do. In the following picture, some of the qubits are given different colors. One is half blue. Doing a B flip here creates a couple of particles on the white squares either side. These are shown in orange, so I'll call them orange particles. Another qubit is light green. Doing a phase flip there creates the other kind of particle on the blue squares either side. These are shown in red, so I'll call them red particles. What about the dark green qubits? Doing phase flips on these, one after the other, would move the top red particles in a loop around the rightmost orange particle. For example, if we first do a couple of them, we move the red particles 2 steps to the left. The next one, which is on the same qubit as we did a bit flip earlier, moves it up past the orange particle. The rest then take it back to where it started. In 3D universes, as we learn, having a particle loop around another does absolutely nothing, but with particles living in 2D, interesting things can happen. Let's see what happens here. First, let's see what we mean by a loop that does nothing. Say you never did the bit flip and never had any orange particles. When all we'd have is a loop around nothing. This is what boring looks like. So let's compare the two following situations. First we do the blue bit flip, then the light green phase flip, then the dark green phase flip. First we do the first with the light green phase flip. Both start with nothing and end up with a pair of orange particles and a pair of red ones. Both had one of the red particles do a little loop. The difference is that the first case has a red particle doing the loop around the orange. The second is boring. Most qubits have just one thing happen to them and don't talk to any other qubits. So they don't really even know if they're faceless or not. The one goes, okay. The important qubit is the one where both a bit and a phase flip happen. In this case, the bit flip happens first, and the second it happens after the phase flip. This makes a difference. I have to remember what bit phase and flips do. The bit flips zeros to ones, ones to zeros. The phase flips minus to plus to minus, minus to plus. But if we have a qubit that is 0, 1 and do a phase flip to that, understanding what happens here would take a wee bit of maths. The maths from this post, in fact, but let's keep it simple. It turns out that it does nothing to turn 0, but turns 1 to minus 1. Well, yeah, that's like applying the Z gate, basically. What the flipping heck is minus 1? It's basically 1 but with a minus. If you ask the qubit whether it was 0 or 1, it would still tell you that it's 1, but if you had superpositions, the minus might do some stuff with the maths, like turning a plus to a minus, for example. Now, let's suppose that the qubit was initially 0 and the flips according to number, and then to the flips according to order number 1. We then, when we first do the bit flip, we get a 1. When we then do the phase flip, we get a minus 1, but it did order number 2. But if it did order number 2 doing the phase flip first, it would do nothing. Then when we did the bit flip, we'd get a 1. So when we do a bit and a phase flip to the same qubit, it doesn't matter which order we do them in. The results differ from some weird mathsy minus 1. The same would happen whether the qubit started as 1 or plus or minus anything. So there's a difference between an empty loop of a red particle and one that goes around the orange one. Particles in the universe, they are anyons. I don't know. So let's go to planet. I don't know. I'm just reading. I'm not fully, I think, grasping all that. The planar code. Fairly short. So far, we've been looking at the toric code, which, as the name suggests, needs to be wrapped around a donut shape. This isn't really the most practical thing in the world. So how about something that can be done on an ordinary flat surface? Something like the following, perhaps. As before, the little white squares are qubits. For each big white square, there's a rule there. Yeah, that all the qubits must obey. Usually they have 4 qubits around them, but the ones on the edges have only 3. Yeah, so the ones in the corners have just 2. Yeah, the blue squares also have a rule that their qubits must follow. All of those have 4 qubits around them. When the rules are broken on any square, we can think of it as a particle nanion. The whole point of the quantum code is to store a qubit and to protect it from bit flips and unwanted measurements. For the toric code, this was done with big loops around the donut. Here, where there are no loops like that anymore, we'll have to work out a different way. One thing we can do is to take the big white square at the top left and stop enforcing its rule. We'll also do the same for the big white square at the bottom right, top left, bottom right. Now these squares are allowed to both have an anion in or both not, because these anions always come in pairs. Now these squares are allowed to both have an anion in or both not. These squares can now be used to store it. One thing we can do is to take the big white square at the top left and stop enforcing its rule. Top left. But there are now these squares. It's also the same for the big white square at the bottom right. Now these squares are allowed to both have an anion in or both not, because these anions always come in pairs. They could also have some superposition of the two. So it's basically just saying that these two behave like if they were close to each other, if they were connected. These squares can now be used to store our qubit. We can have like that. So you also got 3. Okay. These squares can now be used to store our qubit. We can have them both empty for a qubit that is 0, and both we can have them both empty for a qubit that is 0, and both with anions for a qubit that is 1. This is then nicely protected against logical bit flips, as a line of bit flips would have to stretch from top left to bottom right to do any harm. These squares can now... What squares? These ones you're talking about? You're talking about what squares? That's confusing. Now these squares are allowed to both have an anion in or both not, because these anions always come in pairs. They could also have some superposition of the two. These squares can now be used to store a qubit. Unfortunately, the qubit won't be protected from unwanted measurements. To see if there is anyone in the top left square, you only need to look at 2 qubits. The same is true for the bottom right, so it's quite easy to measure our logical qubit. To make it harder, let's knock down the wall between the top left square and its neighbor to make it harder. Okay, no, then, okay. We'll also do the same at the bottom left. Specifically, let's look at the code below. This has a double square at the top left, which is just 2 of the all squares stacked together. Otherwise, it's exactly like a normal square. A rule can be set for the 3 qubits around it, and anyone can live there. The same is true for the bottom left. Now the gremlins need to measure 3 qubits to destroy our superpositions, so it's a bit harder than before. To protect the qubit from unwanted measurements even more, we can just carry on knocking walls down. So we have a big multi-square at the top. Multi-square at the top and the bottom both can hold an anion, but they will be smeared across the whole edge, and so needs lots of measurements to work out which you have. Now we have a good way of storing a logical qubit. This finally deserves the code part of the name planar code. Now that's basically you could check out what is happening from the perspective of the other kind of anions, the ones living in the blue squares, but I'll leave that. Okay. But still this doesn't answer my questions of how do you operate at the physical qubit level, because we talked about how do you represent zeros, ones, pluses, minuses, but not like the stuff in between. You can represent. How would you do that here? It's like, how would you, if that's your logical qubit, like, I don't know what it means to apply an S gate to this thing, right? Is it that you're applying an S gate to all the qubits? Probably. Okay. Yeah, but if you're applying an S gate to all the qubits, it feels you're always representing sort of pairs of, right? So the zeros, 0 or 1, pluses or minuses. Because then it's about the counting the whether it's an odd number of loops, right? For the toric code. Here will be what lines? Not quite sure. Not quite sure if we. I don't quite get why there has to be that sense of like having pluses and minuses. Like, what if you okay, it is probably because of the goal of this is to detect qubit flip errors, and so and that happened with opposites, right? So if you would have say the state of, if you want to apply a NES gate, you have to do it in a way that you're encoding the result of the S state and the qubits. Here, so you're putting a bunch of the opposite, what will potentially be the error. So you have the opposite, like if you would do like the inverse of the S gate. Wait a second, not the inverse. This would literally be the opposite in the block sphere, wouldn't it? If you apply an S gate to a 1, right? Sorry, that would be these, and you apply an S gate. Okay, and if you apply, now I can do that. Yeah, okay, so that's actually the opposite, yeah, in this case. But it's not with these, right? Yeah, that's not literally the opposite. That's like mirror. And I want that. I want that. Maybe. Because that's essentially. No, actually no, because what the bit flip error would do is mirror. So, that's the mirror. So my guess is that you would basically, the result of applying an S operation is that you would have a bunch of the, I don't know how to call the state, right? But I'm just going to a bunch of like S and S minus ones, right? But like that's not really how you would call the state. This is just the operation, but you would have those things. So you literally have the ideas here. You constantly have to have encoded, like the way these qubits are set up is they always have kind of the state in which the qubit is supposed to be in and its opposite, because the goal is to detect the bit flips. That kind of, I don't know if this is the way it works, but it seems to make sense. Isn't there anything else in here in this direction? Otherwise, I'll probably jump to something else in the next video to try to explore that a bit more. Because then there's QD codes. What is that? Planar code is number 13, and then 13, and then there's QD codes. And then there is nothing else in experiment, and then it's kind of the end of this block. So, was it in July? It's fairly old, 2016, right? But QD codes. Oh God. Doesn't. So, computers based on beats. Well, a computer needs to do a lot of classic little pieces of math. The things to specialize can never be too hard. We found some weird rocks that can do it for us. Rocks. By which I mean transistors, which are a bit more complicated than just weird rocks. Okay. It's just a big pile of them. If we use fancier beats that go beyond one, let's call them deets. Then they would do fancy basic beats of maths that might be nice for designing nice and efficient programs, but it might also be too complicated to actually build. We would need even fancier rocks. So we settled for beats in the end. With quantum computers, we don't yet know whether it would be the best to use qubits or some sort of fancier QDs for the rest of these positive things. QDs can be one of 10 possible things. 10 possible things. So instead of just a 0 and a 1, we'd have for qubits, these qubits can be 0 and there's nothing special about 10 except it's a nice number. Everyone lost 10. I think really it's the same that with beats is a convention, right? Because as James here says, basically you could build computers that you don't use beats, but like I think they're called treats, and I think there's an actual computer built on this. And with qubits, this is just a convention because if I remember well, I hope I'm not saying anything wrong, but I remember reading that the way this is implemented is using the fact that, like for example, electrons have different energy levels, but they actually have more than two. They have many energy levels, but for the sake of simplicity in terms of implementation, only two levels are used, and those would be the zeros and the ones of the qubit, I think. Okay, yeah, but that's not one. Yeah, but then the whole thing becomes messed up. So quite as simple as loops. I don't know, some weird things in here. Blue squares. Yeah, it's not what I. No. Okay. I don't know. I'll do a bit of extra research. See if I find other reading material on this. Something maybe closer in time, but it really Yeah, I think, I mean, I got the intuition and I understand most of the stuff, but I'm not, I don't know, I don't feel like I could leave the topic aside for now, almost, because I really don't feel like digging into this a lot farther. It's at a generic and intuitive level, basically, it's a mechanism to, define, it's a mechanism to implement qubits in a way that we can easily detect errors and then correct them. So it's pretty smart. Um, it's pretty smart, but I was missing. I'm missing a bit of extra stuff on more info on how this actually works. I don't know if I'm right when I say about the S and the S and the opposite states. We'll see. Let me do a bit of research and see if I can make another video on that.